Good morning, friends. I am Professor Suresh Charola, working as an assistant professor in the Department of Electronics and Communication at Marwadi University. Today, in this tutorial lecture, I am going to discuss about the PN diode. So let us start with the basics of the PN diode. Okay, if I divide the semiconductor, for example, silicon and germanium, it is divided into two parts. One we call the intrinsic semiconductor, another we call the extrinsic semiconductor. In intrinsic semiconductor, if you look, all the electrons, all the electrons of the silicons are joined with a covalent bond. Okay, and there is no extra free electrons and there is no extra free holes. That's why the material we call as a intrinsic semiconductor. If you look at that extrinsic semiconductor, there are the materials which is made up of semiconductor, but extra impurities which has been doped, that is a p type, and extra impurities in a semiconductor that is doped, that if it is free electrons, then it is called as n type material. For example, let's suppose take a n type semiconductor. So this is nothing but an intrinsic semiconductor, and here if I dope this material with a pentavalent impurities, pentavalent means there are the 4 electrons around the silicon and there is a 1 free electrons which is there inside the atomic structure. That means the current which is flow inside due to the n type of semiconductor due to the electrons, because the free electrons are there, and that's why this material, intrinsic material, has been converted into the extrinsic material. Now let us take the example of the p-type semiconductor. In the p-type semiconductor, again this is nothing but intrinsic semiconductor. There is no free electrons and there is no free holes are there in intrinsic semiconductor. But once I will dop with the trivalent impurities which have 3 electrons around the atom. So this one is a 1, this one is a 2, and this one is a third electron. And there is no 1 electron, that's why we call as a holes. So when you dop the material with a trivalent impurities, you have a number of free electrons in atomic structure, and that's why this material has been converted from intrinsic material to the extrinsic material. Now what happens when we connect both the materials together? Do you have any idea? Okay, before going to the connect the two p-type and n-type material together, we'll just discuss about the symbolic representation of the p-n diode. Here if you look at, there are the two regions which is connected, n-type and the p-types together. If you look at the schematic representation, here this line indicates is nothing but a cathode, another side that is nothing but an anode. That means this will be the p-type and this will be the n-type. So in the physical component, if you look at over there, the small silver line indicates that is nothing but a strip marks that indicates the cathode. The another we have a anode. So this one is nothing but a symbolic and the systematic representation of an p-n diode. So now let us connect the p-type material and the n-type material together. Here I am considering one case 1 when I had not given any bias voltage across the p-type material and the n-type material. So this will be the equivalent circuit when you don't apply any bias voltage across. So the current which is flowing inside the circuit, that will be equal to 0. P-type and N-type, and I had applied a small forward voltage across the P and dot. What happens? These electrons which is sitting in the N-type region will get energized and will try to move on the P-type region, because there is nothing but empty space, there is nothing but holes are available in the P-type region. Again these electrons will try to jump and cross the region and again recombines with the holes. That means electrons which is majority in the n-type and the holes which is majority in the p-type will recombine together, and the situation arises that situation is nothing but this. In this region, if you look at in this again, in this deflection region there is nothing over here except the acceptor ion and the donor ion. Okay, there is no free electrons and there is no free hole charge are there. Still equilibrium state doesn't exist. What happens again? These electrons at the voltage what you had applied, these electrons have that much of energy that it can able to cross the junction and can reach to this hole. Again same, these electrons have a energy to cross the junction and receive, and again it go to the p-type region. That's why the situation what arises, the deflection regions have wider and have some deflection region at certain voltages. This is what the condition when you apply a small forward voltage across the p-n diode when you connect the two material, that is the p-type and n-type materials together. Now the region in between we call in between the p-type and n-type, because there is nothing extra except the acceptor and the donor ions there is no free electrons and there is no holes. That means it can be said as a space charge region, or it also calls a deflection region. Again, the name we call as the barrier in between the P type and the N type. That's why we call it barrier potential, or we call it built-in potential. Now if you look at over here, when I apply a small forward voltage, again if I increase the voltage across the P and diode here, look at over here, the P type of DC battery had connected to the P type material, and the N type negative terminal of the battery had connected to N type material. Now this diode is nothing but in the forward bias. Okay, now what happens? The electron here, due to this positive charge of the battery, this hole sitting on a P type regions will get opposed, and it will try, we are sitting in the P type region, holes will get opposed and try to cross over this junction. But here this holes doesn't have that much of energy to cross junction. What happens? This holes will try to cross over the deflection area and sit over here. Again this also will sit over here, this also will sit over here. Again these electrons, due to this negative charge of the battery, it can oppose and it can sit over here. That means what is the situation? The first situation what we had seen, that has been erased. That means now the deflection region will reduce it. So now this all the electrons, when the deflection region get reduces, this all the electrons sitting on the N type region will have energy to cross over the junction, because the deflection regions get smaller. So when the bias voltage is applied, the majority charge carriers will recombine and allow the current flows to the, because why the P to N? Because this electron is moving in this direction. So you know about the current is always be opposite to the electron. So current will flow in this direction from P region to the N region, and that's why the current which is flow from P type to N type region called as a diffusion current. Now when the diode is in forward bias, and if you connect the multimeter across the P N diode, what happens? The current is flowing from the P type to the N region. When you measure the voltage across the P N diode, here, look at this situation. If the diode is made up of a germanium, and if you find the voltage across the diode when the diode is in forward bias, the voltage what we arrived, that is nothing but a 0.3 volt across the P N diode. If the diode is made up of a silicon, then the voltage which is across the diode, if you measure a voltage across the diode, it will be gives a 0.7 voltage. That means my diode will get forward bias at 0.7 voltage if it is made up of a silicon, and PN junction will get, PN diode will get forward bias if it is made up of a germanium diode at a 0.3 voltage. Now let us connect the PN diode in a reverse bias. When you connect the diode in reverse bias, the N terminal of a battery is connected to the P type of material, and N type of material which is connected to the positive terminal of the battery. The voltage what we have, right, that is nothing but a reverse voltage. Now what happens, due to this negative holes sitting on a P type region will get attracted to move, will try to move on a negative terminal of the battery. Here, this electron which is negatively charged, due to this positive charge of a battery, these electrons also will get attracted to move at the positive terminal of the battery. So if you look at all these holes sitting on the P-type regions will get attracted and will move, and all the electrons which is sitting on the N-type regions will also move in a particular direction. Okay, now if you look at the condition of the deflection regions, when these holes will move on this direction, there is nothing over here. That means the deflection regions get wider in this case. But look at over here, there is a small amount of current flows. What is the reason to flow the current? Look at over, what should be the minority charge carrier in the P-type regions? That is nothing but a electron. What should be the minority charge carrier region in N-type material? That is nothing but a hole. So I have electrons over here and I have a hole over here, that is a minority charge carrier. Here, if you connect a battery that is a N-type and the P-type battery to the P-type material, what happens? Due to this positive charge, this hole is nothing but a minority charge carriers will get opposed and it will try to recombine with the electrons which is sitting in the P-type region, and due to this current flow, that is called drift current, and this current when a reverse voltage when you apply, the minority charge carriers present in the deflection regions will recombine and allow the currents to flow from N type to the P type, because electrons is a minority charge carrier over here. So electrons moves in this direction. The current will always flow from N to P region. That's why the current flows from N to P region. That current we call, and that flows due to the minority charge carriers. Now if I draw the ID characteristics of a PN diode, on x-axis I have the voltage across the diode and the current which is flowing inside the circuit. So if the diode is made up of silicon, it small amount of current flows due to the small amount of recombination. When you go on increasing the voltages, what happens? The current increases nicely, and this voltage 0.7, that is nothing but the voltage across the PN diode. Here, if the diode is made of germanium, that means at this voltage 0.3 voltage, the characteristics will, that means the diode will be forward bias at 3.3 volt for a germanium diode and 0.7 voltage for a silicon diode. When you apply the reverse bias, that means the current and the voltage both are negative, and here up to certain extent there will be no current will flow. There is small amount of current will flow due to the minority charge carrier, and that current we call as a reverse saturation current, or we also call as a drift current. Now when you exceed some voltage, let's suppose R, the reverse voltage, when you go on increasing the voltage at one particular of the voltage, the diode, the minority charge carrier increases in a more amount in a deflection regions, and that's why at certain point there is a large amount of current flows in a circuit and diodes get burned out. So you must have to take care what should be the voltage, minimum voltage should I give to the diode which should when it's a reverse bias. If you look at the equation of the ID, that is a Is e raised to Vd by n Vt minus 1. Why is the exponential function? Because if you look at the graph, what I have, that is nothing exponentially. That's why we have exponential function in the equation. Here the Is stand for saturation current, and you know the saturation current always flows when the diode is in reverse, bias. Okay, and the Vd is nothing but a forward bias voltage across the diode. Here Vt is nothing but a thermal voltage which will be determined depends upon the temperature. Here look at the equation of the Vt. Vt is nothing but a K Tk by Q. Q and K. K is a Boltzmann constant. The value is 1.38 into 10 raised to minus 23 joule per Kelvin. And here the temperature. Depends upon the temperature, the value of Vt, the thermal voltage will change, and the Q is nothing but a charge, that is a 1.6 into 10 raised to minus 19. Now there is a one unknown term that we call as a N. Here the N value varies from 1 to 2. If the diode is made up of an silicon, the value of N that will be equal to 2. If it is made up of a germanium, the value of N that will be equal to 1. Let us summarize what we had studied in terms of the phase, what we had discussed throughout the session. So what must be present in the deflection region in the PN diode? You know about the deflection region, there is no free electrons and there is no holes. So what will be present over there? Only immobile charge carrier. That means the charge carrier which doesn't have a free electrons and the free holes. So which current will flow to the majority charge carriers? You know about the majority charge carriers recombines in the deflection region, and that's why the current we call as a diffusion current. So another next question, tell which current flows due to the minority charge carrier. You know about the minority charge carriers. Minority charge carriers are always flows in the deflection region due to the minority. Okay, so current which is flows due to the minority from N region to P regions we call as a drift current. So what is another name of the deflection region? There are the four names what I had discussed. One name we call the space charge region, because it is space which separates the P type and the N type material. That's why it was a space charge region. It also occurs a deflection region, and nothing but its barrier in between the P type and N type. That's why it's called barrier potential, or we call it a built-in potential. What is the value of resistance when the diode is in forward bias? You know when the diode is in forward bias, the deflection region is very small. in between the p-type and the n-type material. That means this electrons which is sitting in the n-type and the hole sitting on the p-type will easily cross over the junction. That means there is a less resistance when the diode is in forward bias. So almost equal to 0 ohm, that is less, it's always be the ohm. So what should be the resistance when the diode is in reverse bias? You know, when the diode is in reverse bias, in the PN diode, what we have, you look at the deflection region. Deflection region is wider. Deflection region is wider in a PN diode. That's why the resistance, this electron sitting over here cannot able to cross over this junction and reach to the p-type region. That's why the junction which is in the reverse bias have the highest more resistance compared to the forward bias. So almost infinite, or you can say it's in the mega ohm. Thank you for listening. I hope you enjoyed the video. Thank you once again.